Okay, welcome to our discussion of the conservation of momentum law and collisions. So let's first start off by stating that when there's no forces that are acting on an object, then the momentum of that particle is going to remain constant. So if F equals 0, then the momentum is basically constant. So think of momentum as a quantity that can be conserved if there are no external forces acting on the system. Now earlier we had derived Newton's second law, sum of F equals ma, and written in this alternate form of change in momentum over change in time. We replaced the acceleration with the change in velocity over the change in time, and then we realized that mass times change in velocity is really a change in momentum. So really Newton's second law can be written as the sum of the forces equals the rate of change of momentum. Now this is important because this will really explain the conservation law. You see, if the sum of the forces is 0 on a system of particles, such as like two objects that are interacting with each other in a collision, then we know that if this side is 0, then the right side must be 0. So the change of momentum of the system must be 0. That means that the final momentum minus the initial momentum must be 0. Hence, the initial momentum of the system before and the final momentum of the system are the same. And when I talk about the momentum of the system, I'm really referring to the total momentum of all the objects that are interacting with each other. Now we're going to be applying this conservation of momentum law in collisions. And whenever you want to state the conservation of law, which is the conservation of momentum law, which states basically if the net force on the system is 0, the total momentum of the system remains constant, you can simply write this statement right here: momentum initially equals momentum finally. And the grader will be understanding that as you stating the total momentum of the system is remaining constant. So up to this point, we've studied the motion of a single particle or object, and as it underwent some force and time of impact, and we looked at the change in momentum and impulse. Now we're going to be looking at two objects, for example, that are going to approach each other and interact by the means of force or forces. So that is a collision. So a collision is basically when two or more objects come together for a short time interval and there are forces acting on them. Now the collision time is very short, and when the velocities change from that initial to the final value. Now there really are two types of collisions, as you'll see here. I've written three collisions, but really two of them are considered together. So this is really inelastic. So we have really two types of collisions. We have elastic and we have inelastic. What's the main difference between inelastic and elastic? The elastic collision is a collision where the energy of the system is the same before and after the collision. So the energy is conserved. And we also know that the total momentum is conserved. In an inelastic collision, this is a collision where the energy is not conserved. Some of the energy is lost in other forms of energy. So some energy is lost, and examples of that would be, for example, heat and sound and other types of energy, light, for example, but most of it would be probably heat. So in this type of collision, the total momentum is also conserved. So in both types of collisions, the momentum is conserved of the system. However, the main difference between an elastic collision and an inelastic collision is the elastic collision is the only type of collision where the energy will be conserved. There is also another special type of inelastic collision, and that's called the perfectly inelastic collision. Some books will call it the completely inelastic collision. And in this kind of collision, that's a situation where two bodies stick together after the collision. And even if you have two bodies that would normally be in elastic collision, but then they get stuck together, there is no way that they would be elastic. So anytime you have a situation where the bodies stick together, that would be considered a perfectly inelastic collision. So there's some little pictures here to show you as well. Over here, typically billiard balls are close approximations to elastic collisions. And then any kind of other collision where objects stick together, this is just a picture of a fish eating another fish, so they're going to be one combined body. That would be called a perfectly inelastic collision. And any kind of like car crash, for example, where you have sound or heat generated, that would be an inelastic collision too. So take a look at the chart down below. This kind of summarizes the differences between them. Is total momentum conserved in an elastic collision? The answer is yes. Is it conserved in a perfectly or completely inelastic collision? Yes. And also in an elastic collision. So all of these collisions will have conserved momentum as long as the net force on the system is zero. There's no external forces acting on the system just before and just after the collision. Is kinetic energy or energy conserved during an elastic collision? The answer is yes. What about it for inelastic collision? And the answer is no. What's so special about certain ones? Well, I would say that the elastic collision is the only one to conserve kinetic energy. And the perfectly or completely inelastic collision, the objects stick together. There is a good point mentioned down here that says that it is important to realize that the total momentum of the system may be conserved even though the kinetic energies of the individual parts will change. So when is momentum of the system not conserved? Well, that occurs when the external force on a system is not zero. So for example, if you have a system here and you have a bunch of bodies that are moving around, particles that are moving, bouncing around in here and colliding with each other, then internally the momentum is not conserved. If we were to look at these individual bodies, they're changing their momentum as they strike one another. However, if you were to look externally on this whole system and there were no forces acting on this whole object externally, then the momentum of the whole system would be conserved. So that means that if you were to add up all the individual momentums of the system before and then later on at another point in time, it would remain constant. But individually, the particles internally would be very complicated and the momentum is not conserved because there are external forces acting on these particles individually. And that's it for our discussion about collisions and the conservation of momentum law. Now you can proceed to do some problems involving collisions.